Hello, everyone. My name is Rebecca, and I am part of the marketing team over here at Tech30. I would like to thank everyone for attending this webinar. Today, we have Trevor Silence, who will be giving a live presentation on calculus integration. We also have Ron Zabilski, who is a solutions consultant for Tech30. And just to remind everyone, if you have a question at any time during this webinar, feel free to leave it in the question or chat box, and we will do our best to answer these questions at the end of the webinar. With that being said, I'm going to pass it over to Ron, who will give a little background of who Tech30 is and what we offer.
Thank you, Rebecca. As we conduct this webinar today, we highly encourage you to engage with us. You will be able to ask questions, leave comments, as Rebecca said, on the sidebar in the GoToWebinar panel. Even if you have questions or comments that don't relate to today's specific topic, feel free to ask them, and we can address them in a follow-up email or in future webinars. And please view us as a conduit to get feedback to the PTC Mathcad product managers and development team. As most of you are aware, Mathcad is more of a niche product within the PTC portfolio than some of the others. So let's build a community. The features that get most requests will most likely be prioritized for future Mathcad releases. So please use this platform as an opportunity to influence the direction of the product development roadmap. We'd also be happy to receive comments and questions by email anytime after the webinar. Just as a side note, for those of you that can take advantage of a current PTC promotion, they have a buy one, get one half off promotion for Mathcad. This provides a 25% off of 2 licenses of Mathcad. And if this promotion is good for you, for any number of 2 pairs of licenses, please give me a call and we'll be able to discuss your use requirements. So with that, let's get to the next slide. As Rebecca said, my name is Ron Zabilski. I'm a solutions consultant with Tech30. And Tech30 is a value-added reseller of PTC software products. Tech30 is also an engineering services company that helps engineers do engineering. We do this with the tools from PTC and other OEMs to help our customers make the most of these tools through training and engineering services. We strive to get to know you and your business. We are at our best when we can actually expand the business of our customers and build a community by connecting them with those who benefit from networking with each other. Next. So the company was established in 2002. We currently have over 80 employees with more than 50 engineers in our offices. Our headquarters is located in Mission Viejo, California, but we're distributed around the US, meeting the needs of our customers. I'm located in the Boston, Massachusetts area. Tech30 also has small business status and 4 business units. First is the PTC software, which we're going to be talking about today. We also represent a number of 3D printing and additive manufacturing companies. We provide engineering services, and we also have a Siemens software arm. We can provide a wide range of engineering services, including mechanical, electrical design, static, dynamic, and kinematic analysis, design for manufacturing, assembly, and 3D additive manufacturing. We can install new PLM implementations, do system integrations and migrations, and we can do training for all the services above. Tech30 can provide services in areas of engineering and design where you currently do not have the expertise, or supplement your existing in-house capabilities. Next. As a PTC value-added reseller, we focus on the products here: Creo, Windchill, Mathcad, ThingWorx, and Vuforia. Next. As I said earlier, we also have a broad portfolio of 3D printing companies that we represent. You can look at these technologies on this page, and I won't go into a lot of detail, but just keep in mind that we focus on industrial case uses for 3D printing in both plastics and metals. We help our customers make additive manufacturing become part of their finished product, or use it for tooling, fixtures, and jigs. If you have any interest in these areas, please give me a call afterwards, and I can have a conversation on your use case. Next. So today's webinar is about Mathcad calculus integration, which is the main reason why you're all here. But before I pass the presentation over to Trevor, I want to inform you of the services that Tech 30 provides around Mathcad. We not only sell the software, but we also provide a unique value-added service to ensure that our customers make the most of their software purchase. First, though, what is the value of Mathcad as a software by itself? The automation and reuse of the calculations is huge. Collaboration, sharing those calculation worksheets in a nearly easily understood document. And the natural math, being able to create calculations as you would on paper that everyone can understand with no coding or development experience required. Next. One of the unique services that Tech 30 offers is our conversion services for Mathcad. Customers often see the value of standardizing on such tools such as Mathcad to make a more collaborative, efficient way within their organization. This will become more evident, especially after you see Trevor's presentation. However, one of the barriers to adopting Mathcad is getting your calculations from other formats into Mathcad. We're all busy at our primary job function, so who has the time to bring legacy Excel files, hand calculations, MATLAB files, or even Mathcad 15 files into Mathcad Prime? That's where Tech 30 can come in. You give us the calculations in whatever format they're in, and we'll convert the data for you and hand you back new Mathcad worksheets. We'll even train your users to use Mathcad and ensure maximum use of the tool. So if this situation describes the state of your engineering calculations, please let us help you. Next. So with that, I'm turning the webinar over to Trevor to show you the different methods of integration of calculus into Mathcad. So it's all yours, Trevor.
Thanks, Ron, for the great introduction. So today we're going to talk about calculus integration. I'm going to start with the challenges of calculus integration. So if you've ever solved a calculus problem before, you know that there can be a lot of steps in the process to solve these problems. There's a basic example of what a derivative and integral type problem would look like graphically represented. And so for these problems, you must remember common integration processes for shortcuts, or you have to have a pretty strong theoretical knowledge of how to do derivatives and how to do antiderivatives or integrals. Here's a list on the right-hand side of some common derivative and integral definitions that are very helpful when trying to solve these calculus problems. And if you've ever written them down or you've ever tried to read someone else's, it can kind of be cryptic to understand all the different terms and functions, and just the writing itself can kind of get confusing if you're writing it on paper. So these are some challenges with traditional calculus integration done by hand. So some capabilities of Mathcad for calculus integration. You can do integration, you can do differentiation, you can even solve differential equations in Mathcad. And they're really easy to write. It's basically just like typing it out as you would a Word document, but it'll solve the problem for you and save you a lot of steps and a lot of time. And it's also really easy to disseminate this information to your colleagues in an easy to understand way. So instead of them having to decipher or what you've written down, they can just read it directly on the paper as if it was written in a textbook. And I do have on the right-hand side the fundamental theorem of calculus that's proved by using the Mathcad functions and techniques. So some values of doing calculus integration within Mathcad is you can reduce the time and confusion when actually making these and distributing these calculus solutions to your engineering problems. You can also utilize the built-in functionality and techniques to improve the sharing of solutions between your colleagues and anyone else who needs to understand where you're getting the numbers and solutions. Now on the right-hand side, I have an example of an integration using symbolics and also ordinary differential equation being solved in a solve block. And so with that, I'd just like to hop right into Mathcad and go over some ways to do these derivatives and integrals and these calculus functions. So if you have the empty worksheet that we provided, you can follow along. I'm just going to be filling in the gaps here. So the first one we're gonna talk about or do is how to find a derivative an expression that contains the arctangent function. So this one can be, you kind of have to remember it, or you have to work through a lot of steps in order to solve this, usually. But with Mathcad, it's pretty easy. So I can add the operator for differentiation, for a derivative, by clicking on the operators and then clicking the derivative button here. Alternatively, I can also just hit Control-Shift-D as a keyboard shortcut for that. And then I can just go ahead and define this as a derivative with respect to the z variable. I'm just going to do a first derivative, and then I'm going to put in parentheses here z times a tan, which is arctangent of z. And then I can go to this side, and I can add a symbolic operator, which is found under the symbolic tab. It just looks like an arrow. And so when I add that, Mathcad is going to work its magic, and then it'll produce a result where we have a result is a tan arctangent of z plus z over z squared plus 1. So there's a whole lot of steps that are happening between these two that you're not really seeing, and that can save you a lot of room on your paper and make it easier to follow for other people as well. For the next one, we're just going to use kind of the same process, but we're assigning it to a function f. So when we actually get the result here, so if I were to just throw in that symbolic operator, I'm going to use the shortcut control period. You can see that it produces the result 4 times x. And if you notice, this f of 2 now populates with 8 because we've defined the function f to be equal to 4x. So when we plug in 2 for x, we get the answer out 8, just as expected. We'll also be taking the derivative of a sine function with a complex argument. So for this one, I'm just going to throw the symbolic evaluator in there as well, and Mathcad's going to do the work for me. So it really is just setting up this derivative operator in front, and then defining what you want to take the derivative of, and then Mathcad does all the hard work for you and gives you the result at the end. So for example, in this one, if we solve it, it's just going to be in a polar format, just like above. But if we wanted to switch this into a rectangular or Cartesian format, you can just type it right here, rectangular. And then Mathcad is going to convert that into the rectangular form by adding a hyperbolic sine, hyperbolic cosine as necessary. You see there is still an imaginary part, but it is in a rectangular format for this one. It's also possible not just to solve derivatives, but integrals. So to solve integrals, what you can do is you can add a integral operator. Similarly to how you add the derivative operator, you can add the integral one right next to it. The shortcut for this is Control-Shift-I. So for this one, we're using an indefinite integral, so I don't actually have to define the boundary or limits here. So I'm just going to type e to the x power, and I'm going to multiply that by sine of x. And then I'm going to take this integral with respect to the x variable here, and I'm going to toss in that symbolic evaluator once again. And so now we have our results, which is just e to the x times cosine x minus sine x over 2. So you can see really easily, really quickly, we have this solution to this problem here. I'm going to do another one. This time I'm going to have limits of integration. So I'm going to hit Control-Shift-I here again. And this time I'm going to put boundaries in. So I'll have 0 to 1. And I'll do the same thing, e to the x times sine of x. And then with respect to the x variable again. And then I'll evaluate it. And we should have a result that actually evaluates to an answer. So if I have this result here, I can even get just a floating point number by just expressing it and by hitting the equal sign. If I do want to specify how many points I have, I can do the symbolic evaluator again, and this time I can type float, and I can specify what decimal place or how many decimal places I'd like to have in my solution. And so when I evaluate it, I do get this 0.9093307, which is 7 decimal places. And I can just change this to reflect however many that I'd like to see. The last one I'd like to do for derivative and integration is how to evaluate expressions that have parameters in them. So for this one, I'm going to add this integral operator by hitting Control-Shift-I again. and I'm going to have my bounds this time from 1 to c. So I'm actually having a variable in my limits there. And then I'm going to have x to the third, and then we're going to integrate with respect to x again. So if I evaluate this, just like it did with a numerical limit, it just substitutes that c in for the upper limit there, and so now you have a parameter nested right inside of your integration. In this example, it's an indefinite integral, but we have no numerical values, just the variables. And because we're integrating with respect to x, this a will just be carried on as a parameter into your solution. So pretty much anything you can do on paper, you can do in Mathcad. It'll save you a lot of steps. It'll make it a lot easier to read and a lot easier to do. Our next section is limits. So for this one, we're just going to evaluate limits of an expression. So to add a limit here, you can go back into operators, and right next to that integral sign, we have our limit here. So I can just click the button with the limit, and then I'm going to have x as it approaches 0. And then we're going to define what we're actually taking the limit of. So for this case, it's going to be sine x over x. And then I can do the symbolic evaluator again, and we have our limit as sine x over x approaches 0. Our solution is 1 there. So for limits, you may need to remember some other special techniques, especially for certain sine x over x, you have to do a harmonic type limit evaluations. But for this one, we're just going to do a left and right-handed side limit of h of x. So likewise, I can add the operator in as I did before by clicking the button, or I can just go straight down here and hit Control L, and it'll populate that operator. And we're going to do the x variable again, but this time we're going to specify whether we go to the positive or negative side. So I'll just put in minus here. And then I'm going to use just a generic function h of x, and then I'll evaluate it symbolically. And you can see it substituted that p in there. If this was a number, we would get a different result. And depending on this function, if it was like a Heaviside or direct function or something, you may get a different result for both positive and negative sides of the limit. But for this case, since we just have a really generic hx or hp, you're just going to get the same result on the output. The next part I'd like to talk about is series. So if you've ever expanded a series, there can be kind of an involved process if it's like one of your first times or you're not super experienced with it. So this is where Mathcad kind of helps out as well. You can evaluate a series just by using that symbolic evaluator and typing series there. And so you can see this just breaks it up. And by default, it does a Maclaurin series. So you just have x and then minus your x cubed plus x to the fifth. And then we can also specify exactly how much of the series we want to see. So we're going to specify the x variable here, and then we want to go up to the eighth exponent. So now we have an extra term here, x to the seventh over 5040. So this is a way of specifying the precision of your result by setting up this number 8 here. So likewise, I could go to 10, and then I'd have this ninth exponent populated there as well. If you do want to expand a Taylor series, we'd have to specify what point we want to expand about. So I'll just evaluate this with the symbolic operator again, and I'll hit series. And this time I'm going to use x, and I'm going to use my conditional equal sign, which is control equals. You can also find that under operators, under the comparison. So it's equal to sign right here. And this will normally compare things, but when you use it in symbolics, it's actually a definition. It has a special functionality in symbolics and solve blocks. And we will touch on solve blocks a little bit later. But I wanted to emphasize that this is not just your normal equal sign or expression or evaluation here. So this is actually a special one that they use mainly for like a judgment if it's 1 is equal to 1 or some variable is equal to another variable. In symbolics and solve blocks, it does have a special use as just a regular equal sign. So now that I've specified the point that we are oscillating about, this symbolic evaluator will expand the whole function into a Taylor series. about the 0.1. And you can see this goes on quite a bit. So we're just going to keep this small. I'm going to shrink my screen size back down. You can also evaluate a function in more than one variable. So this is e to the x plus y. And so we're going to do another Taylor series expansion, but we're going to specify a point here. So to do that, we have to specify both x is equal to 0, and then we also have to specify the y point. So y is equal to 1. And then when we do that, you can see that this Taylor series has been expanded when x equals to 0 and y is equal to 1. And likewise, it does get a lot bigger. So we're just going to keep this down here so it'll fit on one page. And for the last one, we're going to do this. We're going to show a floating point number for each expanded term. So it's going to be similar to the one we did previously, where we have our series, and then we have our x is equal to 0 and y is equal to 1. But I'm going to hit Shift Enter to create a new line. And this is equivalent as hitting comma, but it just makes it so that you're not expanding so much in the horizontal space. And then I can type float and comma 4 here. And then this will convert each term of this Taylor expansion into its actual numerical result. So you can see what numbers you're getting out of it. Okay, so that's all I got for the limits and series. I'm going to hop over to partial fractions now. So for partial fractions, it's similar method where we're using that symbolic evaluator. This time I'm just going to type parfrac, which is a shorthand for partial fraction. And so we're actually decomposing this expression here, and we're getting it into these terms. This can be useful if you're trying to get like a transfer function for something, or if you have to just decompose partial fractions for some other use. We can also do a partial fraction decomposition on a range function, which is the sign defined here with a 4 on top and n below it. So for this one, I'll also type partial fraction. And since there's two variables in this range function, x and n, I'm going to specify that we want to do the decomposition with respect to x. And so with that, it's going to break it up into the terms that can be combined to make up this range function here. The next one is partial fraction decomposition when the terms are already separated here at the bottom. So I'm just going to type out that symbolic evaluator, type partial fraction, and it's going to break it up the best way as possible for me. So if you've ever done a partial fraction decomposition, this can take a little bit of time to do on paper, depending on the equation, the expression you start with. So it definitely saves you time to do this in Mathcad. And we're going to decompose this further using square root of 2. So you can also add this in using your operators here by going to the square root sign, or you can just use your forward slash, and then this will add the square root here, and then I can evaluate it like so. So this is just specifying what number you'd like to have on top. And by default, it's 1 or whatever it has to be for that expression, but you can actually specify which number you want to see up there if you need to. So you can do this again for partial fraction. In this case, I'm just going to do 1i, which is a complex number, and then it handles the complexes just as well as it does any rational number. And for this example, we're just going to fully decompose this rational function over the complex domain. So this may be useful in like signal processing. You may need to do a partial fraction decomposition on something like this. So for this one, we're going to actually define domain as complex. And oops, I missed too many x's there. Complex. And so you can see it breaks it out. We have some square roots of 2 on top, and then we do have some of these complex numbers here as well. So this is just going to expand it as best as possible when you specify your domain as complex. And if you want to know what other things you can put on top of your symbolic operator, there's a whole list of keywords here. There's a whole list of modifiers. We did do a webinar in the past on symbolics and solve blocks. And that's actually our next section is solving ODEs. And so the way that we're going to solve ODEs today is using a solve block. So these are pretty useful. They used to look different in Mathcad 15, but in Mathcad Prime, they kind of added a little bit of a user interface upgrade for solve blocks. So for this one, we're just going to solve a mass spring damper system. I have the function defined here, f of t, and this is the oscillation for that system. And then this is the actual the force for the system. And then we have our mass is equal to 2, our spring constant k is equal to 8, and then our damping coefficient c is equal to 2. So if I were to type this out, I can have mass times x. And so I'm going to add a derivative. You could either do the Control-Shift-D as we did before, or there's an alternative where you can add a prime operator. And this is done either through the operators drop down here, or you can just type Control apostrophe. So I want to do the second derivative of x with respect to t. And then we'll do another one. And this is going to use our damping coefficient, c times x derivative t. And then the last one will include our spring constant. So it's k times x here of t. And then, like I said before, we're going to need to use the actual conditional or comparator equal sign by hitting Control equal. And then we're going to define our force function here, f of t. Okay, so we have our equation defined that is going to dictate how our spring damper system will behave. And then we're going to give it some boundary conditions. So when x is equal to 0, we know that it's equal to 1. And then when x prime is equal to 0, we know that it's equal to 0. And so the last thing we need for this, after we have our equation and we have our constraints, we want to have a solver here. So I'm just going to type x, and then ODE solved is a solver that we use to solve ordinary differential equations in a solve block. And then I'm going to type the function that we want to solve for, and then how many points within that function we're trying to solve for. So in this case, we're going to do 20 points. And so if I let it do its thing, you can see we have this graph here now, where we have the function x of t over the t vector, and then the t vector we have defined only goes to 10. But since we have 20 points here, you can go even farther than that if you need to. And for the last example for our worksheet is how to do a system of ODEs. So in this case, you have more than one ordinary differential equation, and you're trying to solve all of them at the same time. So I already have this typed out for us, so we don't have to go through and type everything out again. You see we do have the derivative operators here instead of the prime ones. We also have some constraints defined where we have y0 of 0 is equal to -1, y1 of 0 is equal to 0, and then y2 of 0 is equal to 1. And so for this one, to solve it, we just need to have an array here instead of just a variable. So we'll have f, and I'm adding a new line by hitting Shift-Enter, g, and then I'll have h as well. And then I'm going to use the definition equal sign operator, and then I'm going to type ODE solve. And then in parentheses, I'm going to also put another array or vector. And this one is y0 of u, and then I have y1 of u. And then the last one, Shift-Enter, is y2 of u. And then I'm going to have to go through and give it a t value that we have defined above as 10. This is the amount, how far we're going to solve this for. So like we did 20 before, we're only going up to 10 for this one. And then we're going to put how many steps we actually want. So in this case, we're going to do 1,000 steps. So between 0 and 10, you should have 1,000 different points in between it. And this should give us a pretty good curve. So you can see our results on the right-hand side here. We have our three functions, s, g, and h, that we solved for. And they come up as red, green, and blue, respectively. And so you can see this will save you a lot of time instead of having to kind of go through this on paper and write out all the steps. If you know how to define this in a solve block, it can save you time and effort, and it's a lot easier to communicate this information to your colleagues or anyone else that needs to access these documents. That's all I have for the Mathcad document. I'm going to go through some considerations if you are going to be solving calculus problems with Mathcad. Tolerances can definitely affect the results of your definite integrals. So when you have boundaries on your integrals, your tolerances are going to affect the output. So in the first example, we have a decent tolerance, 0.001, and you can see we get a pretty good result. It's practically 5. It is a little bit higher when you go out to these decimal places at the end here, but it's pretty close to the correct answer. If we do reduce our tolerance or increase it to 0.1, then we do get a result that's less accurate. And likewise, if we do have a really precise tolerance here, then we get a lot of decimal places at 0, and we just have this 1 at the end here. So if you are getting some strange results, I would check your tolerances, make sure they're all correct. Something for discontinuous functions, this function defined above is actually discontinuous around the point 12, I believe. So if you see when we try to actually integrate this using our integration 1 of x from -1 to x with our function x here, we get a pretty good result for most of it, but then as it gets up to this point 12, it kind of behaves strangely. And then around point 14, point 15, we get this really big jump. So this is actually the discontinuity right here at that point 15. So for this case, we'll have to split this up into two different integrals. So we'll have our integral 2 here, and then we have an if statement, which actually splits up this integration into 2 different parts, depending on which position we are at within the function. And you can see our result here is a lot cleaner for this red line. So the blue line is the same, because that's our input function, but our red line definitely changes. And then at this 12 point, you can see it's a smooth curve here. There's no jumps around like the previous one. A last consideration is your range must be decreased in order to provide a correct result. So for a narrow function like this specifically, what Mathcad does is it'll go to points and try and get you a result based on that. But if you have a big range where like 95% of your function is 0, it may miss this peak altogether and just assume that the answer is 0. So it's really important when you have these narrow functions like this that you're actually changing your range a little bit to encompass that. So if you get 0 when you think you should have a number, I would try messing with the range, messing with the limits here in order to get the correct result. And with that, I just have some takeaways from today's webinar. So within Mathcad Prime 5, there are many powerful tools that are built in to help you solve calculus problems. Symbolics, which we talked a lot about today, are really easy to use and can quickly solve derivatives and integrals. And then solve blocks are also very useful for solving ODEs and systems of ODEs. And if you need to solve limits or partial fraction, do some partial fraction decomposition or expand series, those are easily evaluated with symbolics as well. And we did cover symbolics and solve blocks in the previous webinar that you can definitely reference on our YouTube channel. And so with that, I have nothing else for the demo today. Opening it up to questions. Thanks for listening.
Thank you, Trevor. We actually have one question from Bethany Runyon, and her question is, are there any other ways of solving ordinary differential equations besides using solving blocks?
Great question. So there's actually a lot of different ways to solve ordinary differential equations. They break it up into a few different types of equations. So there's about 4 different functions outside of using solve blocks to solve for stiff systems. There's another 4 different functions outside of solve blocks to solve for non-stiff systems. And there's one hybrid solver that you can use as a function as well. Did that answer your question?
Yeah, I think that's good. Looks like there are no more questions. Just as a reminder, I highly encourage you to subscribe to our YouTube channel, as we have previous Mathcad, Creo, and Windchill webinars and tutorials. Follow us on LinkedIn, Facebook, and Twitter as well to be updated on any upcoming events, webinars, and exclusive deals from PTC. Once again, thank you all for attending and have a great rest of your day.